All right, here's the big one. Chapter 5, Chemical Bonding. You remember how big this note packet was, so the review video is going to be probably our longest one, so let's get to it. We started with an introduction to chemical bonding. We did an activity where we were classifying matter based on solubility and conductivity, and that was our introduction to show that based on those two properties alone, whether or not something dissolves in water or conducts electricity, we can sort substances into one of four buckets that eventually became our four types of bonding: ionic, metallic, molecular covalent, and network covalent. We started with ionic, so that's where I'm going to start the review video here. And we'll start with naming ionic compounds. We'll go through the other compounds and then finish up with the properties. So we have the International Union of Pure and Applied Chemistry, IUPAC rules, give us a systematic way to name and write formulas for substances. Remember, the total charge of any compound, no matter how it's bonded together, is zero. By definition, compounds are neutral. For main group or representative monatomic ions, we use the common charges from the periodic table, which we're going to review in a moment. You should know your polyatomic ions. You have to have those memorized, their formulas and charges. And then remember that in the context of the phase of matter, we include next to the formula, if we're writing a chemical reaction, or even if we're just writing the one formula, we should know the phase of matter: solid, liquid, gas, aqueous. We should know that each of those four symbols mean those phases respectively. So binary ionic compounds contain one monatomic cation and one monatomic anion. That's where the term binary comes from. Ionic, we have to understand that it contains ions, right? One cation, one anion. But what we're saying here is that those ions are made up of, or were formed from, one individual atom each. Generally, it's a metal cation and a nonmetal anion. It's not always the case. There are some exceptions like we've seen, but generally that is true. And generally the difference in electronegativity between the two atoms that are bonding is going to be, this is about equal to 2. We should really have greater than or equal to 2. But again, that's only a general rule of thumb, right? Like the compounds don't follow the rules we make for them. We're making rules that seem to fit our observations the majority of the time. These end in "ide," so these would be things like sodium chloride, right? These would be things like magnesium fluoride, for example. Ternary ionic compounds contain our polyatomic ions. Again, if it's an ionic compound, we have ions, but in this case we have one cation and one anion, where at least one of them is a polyatomic ion. These end in either ate, ite, or ide. So something like sodium nitrate, I still have one cation and one anion, but the anion is polyatomic because it's made up of more than one atom. I could have ammonium chloride, where my cation is the polyatomic ion. Or I could even have something like ammonium hydroxide, where the cation and the anion are each a polyatomic ion. We looked at binary molecular covalent compounds. So there's no ions here, right? There's no ions, no charges. Covalent compounds mean that the atoms are sharing electrons. Generally, it's nonmetals and metalloid atoms only, and the difference in electronegativity is usually less than 2. These end in "ide," and the most important thing here is we use prefixes to help us determine, so that someone knows how many of each nonmetal or metalloid atom is present in the molecule. So these would be things like carbon dioxide or dinitrogen pentoxide or phosphorus pentachloride, right, as an example. If we're going to write the formulas from the name, set of rules that we can use to remember, we want to write the symbol for either the atom or the ion, depending on what type of bonding is going on. If it's molecular, we use the prefixes to determine how many of each element we have. If it's ionic, we have to use the charges of the ions balanced to zero charge. Remember parentheses if we have more than one polyatomic ion, and then Roman numerals will be in the name if we're dealing with the transition metal ion where we wouldn't be able to know the charge of the ion by looking at the periodic table. Diphosphorus tetrachloride, I recognize phosphorus and chlorine, non-metal elements, that's molecular covalent. And I see prefixes that are going to help me write this formula. Diphosphorus is P2, tetrachloride is Cl4. Calcium nitrate is ionic. I recognize the nitrate as a polyatomic ion, so it has to be bonding ionically. I write out the formulas for these two ions, and then I use their charges to balance to zero charge. Manganese 2 chloride. The 2 is indicating the manganese has a charge of +2. I can use the periodic table to help me figure out the charge of chlorine. I balance to zero charge. This is another ionic compound. And then lithium phosphide. Be careful, it's not phosphate. That would be my formula for lithium phosphide. Going from the name to, or we're going from the formula to the name, if we were going to write out the name of these. If it's molecular, we're going to name the elements using the prefixes to show how many of each element there are. If it's ionic, we're just naming the cation and anion separately. The only thing we have to remember is to include a Roman numeral if I have a transition metal that requires me to tell someone what the charge is, because they wouldn't be able to determine it otherwise. So PF3, molecular covalent, we're going to use prefixes to write out the name. So phosphorus trifluoride. Remember, the first element does not get a prefix if it's 1. Ni3PO4 2, I recognize phosphate. This is ionic. The cation is a nickel cation. The anion is a phosphate anion, so the name is nickel phosphate. But I have to include a Roman numeral because nickel's a transition metal that can form different charged ions, different charged cations. And if we do some backwards work, I know each phosphate has a -3 charge, and there's 2 of them here, so that would be like a -6 total. There's 3 nickels to balance it out, so each nickel must be +2, so nickel 2-phosphate. And then the last one, CaBr2, another ionic compound, so we're going to name the ions separately. It would be calcium and bromide. No Roman numeral because calcium is only +2, so someone would be able to determine the charge just from that. This sheet is more of a reference sheet for you. Sort of all of the things you need to know in terms of naming in one spot. We have the periodic table here, which is showing us the representative or main group elements and the common charges that they form as ions, +1, +2, +3, -3, -2, -1. We have the transition metal group here, which we cannot use the periodic table for the most part to determine their charge. So these, the elements in green are the ones that get Roman numerals when we name them. And just to recall, zinc, cadmium, and silver are exceptions. Silver always forms a +1. Zinc and cadmium always form +2. So they're in the transition metal group, but they don't get a Roman numeral because they do form a common cation all the time. You should know your Roman numerals and the numbers they correspond to for naming those transition metal compounds. Here are the polyatomic ions you will be responsible for, the covalent prefixes when naming those compounds, and then of course we should have the polyatomic ions memorized by now, but there are some trends in the periodic table that you can use to help you remember. The idea here that when we're looking at the oxyanions, the ones that contain oxygen, that 8 contains 1 more oxygen than ite, hypo contains 1 less than ite, and per contains 1 more than 8. And then we had the hangman here. Remember we said the hangman was hung at 308. That was referring to the elements that are on that hangman. Their oxy polyatomic ions, if he was hung at 308, their 8 version of the ion contains 3 oxygens. So for example, nitrate is NO3, but phosphate is PO4, right? All of the 8s on the hangman have 3 oxygens, and everything else has 4. But again, these are the only ones you need to know. These two are just showing you the trends that are found in the periodic table. We did a lot of organic chemistry in bonding, and on this page is how we were naming organic compounds and writing formulas for those. So remember, organic compounds, all about carbon. Organic compounds contain carbon, hydrogen, and sometimes oxygen and nitrogen. We saw carbon makes 4 covalent bonds, so it can chain to itself. It can form networks. We used the Honk rule when we started looking at covalent bonding. Carbon makes 4 bonds, oxygen makes 2, nitrogen makes 3, and hydrogen makes 1. And generally what we're looking for when naming and writing formulas for organic compounds, we're going to name the longest carbon chain using organic prefixes. A little different from the molecular prefixes. The organic prefixes, the first 4 are different. From 5 on, they're the same. Pent, hex, hept, oct, non. But 1, 2, 3, and 4 for organic compounds are meth, eth, prop, and bute. And the common theme for naming organic compounds is we're looking for the longest carbon chain, and we use the prefixes to name that chain. We're going to look for double or triple bonds if it's an alkane, alkene, or alkyne, and we're going to number where the double or triple bond is in the name. We're going to look for branches, and we're going to name and tell where those branches are using lowest numbers. And then we're going to look at how many of each branch we have by using the molecular prefixes. So mono, we don't use mono in the name, but di, tri, tetra. If I have, let's say, 3 methyl groups in an organic molecule, it would be trimethyl. Or if I had 2 ethyl groups, it would be diethyl. So here are the functional groups that we looked at and that we drew out structures for and that we named. Alkanes were organic compounds that contain all carbon-carbon single bonds. We called those saturated hydrocarbons because they contain the most hydrogens as possible. Alkenes and alkynes are unsaturated because they contain a double bond and triple bond respectively. They could have more hydrogens on their molecule if the double bond or triple bond was broken. Those are some formulas for alkanes, alkenes, and alkynes that if we plug in, let's say, 4 carbons, we can use those formulas to figure out how many hydrogens would be in an alkane, an alkene, or an alkyne. We looked at alcohols. The functional group for an alcohol is an OH attached to the organic molecule, and we number where that functional group is. So if it's on, the first carbon, like in this example, we name it 1-propanol. If that OH was moved to the second carbon, it would be 2-propanol. If it was moved here, you might think it would be 3-propanol, but remember, we number from left to right and right to left, and we take the lowest number we can get. So putting the OH on this carbon would still be representing 1-propanol. It would be just like flipping this molecule over. So we have to be careful with looking at, are we forming an isomer, which would mean I have the same number of carbons and hydrogens and oxygens just bonded in a different configuration, or is it really just like a mirror image or a rotation of a molecule? We looked at aldehydes, and aldehydes were a carbon with a double bonded oxygen and H at the end of a molecule. We don't number those because they will always fall at this end position. So this is propanal, right? Aldehydes end with al. Propanal because there's 3 carbons in the longest chain. We looked at carboxylic acids. Again, like aldehydes, we don't number where this functional group is because it's always going to fall at the end of the carbon chain. This is propanoic acid. Prop from the 3 carbons. Anoic acid is how we end carboxylic acids. Esters have this group somewhere in the middle of the carbon chain. Carbon double bonded to an oxygen and then single bonded to an oxygen on one side. These are probably the trickiest to name. We looked at esterification. Esters are formed from the reaction of an acid with an alcohol. And we always name the alcohol portion first. So here we have methyl and then propanoate. So the methyl portion is what came from the alcohol. The propanoate is what came from the acid. And that's the order we name the esters in. Ketones have a carbon double bonded to an oxygen somewhere in the middle of the chain. So we do number where the ketone group is. So in this case, it's 2-pentanone. Ketones end in -one. pent from the 5 carbons in this chain, and 2 because the functional group is on the second carbon, right? We could number it right to left and get 4 pentanone, but we get a lower number if we number left to right with 2. So we always take the lowest number. And then halides or halocarbons, we number those as well. Could be a fluorine, chlorine, bromine, iodide somewhere on an alkane or an alkyne. In this case, it's 2-chloropropane. So we name the longest chain, which is prop, right? 3 carbons. It's ane because it's all single bonds, so it was from an alkane. And then we have a chlorine on the second position, lowest number, so the whole thing together would be 2-chloropropane. And then amines, we didn't focus so much on naming, but just recognizing if we have an organic molecule that contains nitrogen and nitrogen only with the carbons and hydrogens, then it's considered an amine. The names are also pretty systematic, like this is 1-propanamine, prop from the 3 carbons, amine because that's the functional group, and 1 because the amine functional group is bonded to the first carbon, but you're not going to be responsible for naming those because we didn't spend time naming those in class. And then I mentioned this already, but we should be familiar with drawing different isomers for a given organic molecule, recognizing if 2 or 3 structural formulas or representations are isomers or not of a given molecule. So this wraps up the naming and formula writing portion of bonding. The rest of it was the more conceptual, drawing out representations for different substances, for different compounds, hybridization, Lewis structures, shape, polarity. So I'm going to end this video. We'll do bonding part 1, and then in bonding part 2, I will walk through the rest of this review, Lewis dot structures, all the way to polarity and intermolecular forces.